Hi everyone, I'm Mr. Fullerton, and today I want to talk to you for a little bit about electric fields. Our objectives are going to be to define, measure, and calculate the strength of an electric field, and then to solve problems related to charge, electric field, and forces. So, electric fields are very similar to gravitational fields. The electric force is a non-contact or field force, meaning the objects don't have to be touching. The closer objects are to larger charges, the stronger the force they're going to feel. The denser the force vectors, also the stronger the force. So we're going to use this concept of an electric field to describe what happens to a charge placed near another charge or in that electric field. This imaginary construct that helps us visualize what the forces are going to be on that charge. Now we'll measure this with electric field strength, capital E, which is the amount of electrostatic force you would have for any given charge you placed in that field. And typically we'll talk about a positive point charge. Now, the formula for the electric field strength, E, is the electric force divided by the charge that is felt. Or you'll also sometimes see this written as the electric force is equal to the charge times the electric field strength. The electric field strength is in the same direction as the force. So, they are vectors. Let's take a look at a sample problem using this. Two oppositely charged parallel metal plates, 1 centimeter apart, exert a force with a magnitude of 3.6 times 10 to the minus 15 newtons on an electron placed between the plates. Find the electric field strength. Well, we are given the force is equal to 3.6 times 10 to the minus 15 newtons, and we know the distance between the plates is 1 centimeter. We also know, or 0.01 meters, we also know the charge is the charge on an electron, or negative 1.6 times 10 to the minus 19 coulombs. So to find electric field strength, that's the electric force divided by the charge, or 3.6 times 10 to the minus 15 newtons, over 1.6 times 10 to the minus 19 coulombs. I'm just going to use the magnitude of that charge because I'm after the magnitude of the electric field strength, for a total of about 2.25 times 10 to the fourth newtons per coulomb. There's my electric field strength. That easy. Didn't even need the distance between the plates. Let's look at another one. What is the magnitude of the electric field intensity at a point where a proton experiences an electrostatic force of 2.3 times 10 to the minus 25 newtons? Well, we can take the same basic approach. The electric field intensity, or electric field strength, is the electric force divided by the charge. In this case, that's 2.3 times 10 to the minus 25 newtons over the charge on a proton, 1.6 times 10 to the minus 19 coulombs, the elementary charge. Go through that math, and I come out with about 1.44 times 10 to the negative 6 newtons per coulomb. So there's my electric field strength, or electric field intensity. Moving on. The diagram here represents an electron within an electric field between two parallel plates that are charged with a potential difference of 40 volts. If the magnitude of the electric force on the electron is 2 times 10 to the minus 15 newtons, the magnitude of the electric field strength between the charged plates is, well, we can go back to the same strategy again. We're given the electric force, Fe, and we know that it's an electron. So the electric field strength is the electric force divided by the charge, or 2 times 10 to the minus 15 newtons, over charge on an electron. Since we're after magnitude, I'll just use the magnitude of the charge again, 1.6 times 10 to the minus 19 coulombs. I come out with about 1.25 times 10 to the fourth newtons per coulomb. Again, fairly straightforward stuff. Now, just like when we talked about the gravitational field, with the electric field, we visualize that by thinking about electric field lines. They help us see the force a charge would feel if placed at a specific position in space. They show the direction of the electric force on a positive charge. So if you want to know the direction, you imagine you've got a positive charge, put it in space, the direction it would feel a force, that's the direction you draw the electric field lines. If it's a negative charge, you draw the force it would feel is opposite the direction of the electric field lines. Denser lines indicate stronger electric fields, and less dense lines indicate weaker electric fields. Now, when we draw electric field lines, we have to follow a couple simple rules. Electric field lines point away from positive charges and toward negative charges. Electric field lines never cross each other. They always intersect conductors at right angles to the surface. Stronger fields have closer lines, of course, and field strength and line density decrease as you move away from the charges because it's an inverse square relationship. Let's take a look at some examples. It's kind of complicated when you just look at the rules. When you see how they actually work, a lot more straightforward. On the left here, we have the electric field lines around a positive point charge. In this case, since it's a positive point charge, notice that all of the lines point away from that charge. They start at the charge itself and they're pointing away. That means a positive charge that was placed here, for example, would feel a force in that direction. If it was a negative charge, it would feel a force in the opposite direction. Now, I like to think of these sometimes as if they're sources and sinks. So if you see a positive charge, think of it almost as a hole in space where you've got a blow dryer blowing air out in all directions. The direction of the wind velocity from that blow dryer, that magic blow dryer, shows the direction of those field lines. The same token over here on the right, we have a negative point charge. A positive charge placed anywhere in space would feel a force toward that. Therefore, the lines all point in toward that negative charge. You can think of this almost as the magic vacuum cleaner in space. That is a point charge sucking everything in from all directions. So, two ways to think of these. The positives think of as a magic blow dryer in space. The negatives you could think of as a magic vacuum cleaner in space. Or just remember that the positive charges repel positive charges. So if you put a positive charge in space, it gets repelled by the positive charge, and it gets attracted by the negative charge in space, and then draw the electric field lines in those directions. So those are pretty simple diagrams for point charges. Let's look at what happens when we put two charges together. In this case, dipoles. On the left-hand side, we have a positive and a negative. Electric field lines start at a positive, and they go toward a negative. So you see all of the lines coming out of the positive charge at right angles, and coming into the negative charge. Again, try and visualize in space, perhaps on the left-hand side, a magic blow dryer, a source of air. On the right-hand side, a magic vacuum cleaner, sucking in all that air. You should get the same sort of mental image of what's going on here. Electric field lines start at the positive, and they end at the negative, and they move away from the positive and in toward the negative charge. On the right-hand side, we have a positive and a positive near each other. In this case, the force that a positive charge would feel is still shown by the electric field lines. A charge over here to the left of the left-hand charge would feel a force to the left. It would repel. And same thing over here on the right. If we placed a positive charge here, it feels a force from both of the positive point charges, but it's closer to the one on the left, so it'll feel a stronger force that way and follow that basic path. What would happen if we put a charge right in the center? Positive or negative, all the forces on it would completely balance out, and it would be held there right in space if it's completely, perfectly in the center of those two charges. Positive or negative, they would balance out a net force of 0. So, directions of electric field lines away from positive charges and into negative charges. Sample problem here says, based on the diagram, find the magnitude of the electrostatic force between the two spheres and then the direction of the resultant electrode at point P. And we're given A and B that both have positive 1 microcoulomb, or 1 times 10 to the minus 6 coulombs on them, separated by 0.4 meters, 4 times 10 to the minus 1 meter. Let's see how this would look. To find the magnitude of the electric force, that's K, Q1, Q2, over R squared, or 9 times 10 to the 9th, Newton meters squared per coulomb squared, times charge 1, 1 times 10 to the minus 6 coulombs, times charge 2, 1 times 10 to the minus 6 coulombs, or I can just square this first one, and divide by the square of the distance between them. 0.4 meters squared. When I do this, I come up with a force of about 0.056 newtons. So there's the magnitude of the electrostatic force. How about the direction of the resultant electric field at point P? Well, if you remember, if we draw our electric field lines, they're going to go away from positive charges. So the field lines would probably look something like this. And as they come out toward each other, remember, they head up like that. So what direction would a positive charge at point P feel a force? It would feel a force up. So the direction of the electric field at point P must be up. Have to combine the fields from those two charges in order to see the direction of the electric field at point P. Sample problem 5. In this diagram, P is a point near a negatively charged sphere. What is the direction of the electric field at point P? Well, the electric field shows the direction a positive charge would feel a force. So if P was a positive charge, it would want to get sucked in toward that negative charge. So what is the direction of the electric field at point P? To the left. Let's try one last problem. We're asked to sketch at least 4 electric field lines with arrowheads that represent the electric field around a negatively charged conducting sphere. Okay, let's start off with our negatively charged conducting sphere. And we know electric field lines come into negative charges. So if I wanted to draw 4 electric field lines, there's 1, there's 2, there's 3, there's 4. And you could keep going. If you wanted more than 4, you could add them in as long as they're evenly distributed and all going in toward that negative charge. Great. Well, I hope this was a little bit of help to you. If you're looking for more information, more practice problems, check out aplusphysics.com. Thanks, and make it a great day.